All right, our second lesson in chapter 4 is very short today, and it's basically getting into what we call the natural number e. And we're going to look at exponential functions that are called natural. Now, the reason for this e is that it occurs so many places in nature that mathematicians had to figure out why this constant kept showing up. And it's really just a constant. It's a number on your calculator. So if you find the ln button and hit second ln quick, and it'll say e, and just put a 1 there, e to the 1, and you'll see that e is about 2.718281828, although it is not rational though. It is going to go on forever. So what we're going to do then, today we're going to look at exponential functions with base e. Then we're going to graph them, and then we're going to actually use it. So the first thing to do is just grab your calculator and hit e to the 3/5. And e to the 3/5, according to my calculator, is about 1.822. And we could go on. E to the radical 3. So go ahead and try that. E to the radical 3 is about 5.652 if we go to the thousandths place. So just see that e is just what we call the natural number. So therefore the natural exponential function is f of x equals e to the x. Okay, so let's talk about the graph of one of these. Now, this transformation is looking at the graph of 2 times e to the x minus 1. We can see that it's been moved down 1 from that. So that's our horizontal asymptote, y equal -1. You can also see that every exponential function, even the one with a natural base of e, is the domain is -infinity to infinity. And since the horizontal asymptote is -1, then our range is -1 to infinity. The y-intercept you can see is going to be, I believe, that should be a 2 there, shouldn't it? Let's see, 2e to the x minus 1. That should be 0, 2 then, I believe. Nope, 0, 1. My bad. We got to subtract 1. Because if we put in 0 for x, e to the 0 is 1, 2 times 1 is 2, 2 minus 1 is 1. So that's correct. And again, there's no vertical asymptote. So the transformation is down 1. Okay, now let's apply some exponential functions, shall we? These are two very important equations in the banking industry, investment. These are very simple equations, I might add, but we are applying exponential functions here. A is the amount of money in an account. P is our principal. That's what we invest. That's the money we put in. R is our annual interest rate. That's in decimals. And N is the number of times we compound it in a year. T is the time in years. Okay? Continuous compounding, we just call it PERT. Principal times e to the RT. R is your interest rate, T is your time. Okay? So now, you have to be very diligent when you read the questions. So on this first problem, a rich alumnus deposits $5,000 in a trust fund that pays 7.5% interest compounded continuously. Keyword, continuously. So if you look back to continuous compounding, we're going to use what we call PERT. So that alerts us to what equation to use. The trust specifies that the balance will be given to the college at the end of 50 years. How much will the college receive? Okay, well, this is a simple problem where we're only putting the money in one time. So we use PERT, 5,000 times E. Your interest rate then is 0.075 times T, that's 50 years. And you will literally then just take your calculator and type it in. So a $5,000 investment at 7.5% interest over 50 years, I think you'll be shocked to see how much that money grew to. Did you get $212,605.41? That's the power of percent. Now that is a huge interest rate. There was a time not too long ago, a couple years ago actually, a year and a half ago, before COVID and all the other climate changed, that with investing and things like that you were getting 7-8% in a year from playing the stock market. So that isn't completely out of the realm of possibility. It probably is over 50-year time span though. So that's kind of a made up problem, if you will, but it's a good problem nonetheless. Okay, now a father's planning for his baby's college education. According to current estimates, when this baby goes to college, a 4-year in-state college education will cost approximately $75,000, which is probably going to be a lot more in 18 years. If the father opens a savings account today and estimates that he will earn 7.5% interest a year, compounded quarterly, okay, that's the key. That tells us we use this equation. How much will he need to invest to pay for college? Okay, now we have to see what we're looking for here. And in fact, we're not looking for how much money we're going to have. We're looking for how much money we need to invest if we never, ever put any money away after that. Well, that's probably not going to happen very often. Usually we'll just put $100 a month in it or something like that. But say this guy just wants to know. Okay, so 75,000 is A. We're looking for P. 1 plus the interest rate, again, is very high, 0.075. We're going to compound it quarterly, which is 4 times a year. And then we're going to take it to the 4 times 50 power, which of course is 200. All right, so you're going to do this piece by piece. The first piece you want to do on your calculator is take 0.075 plus divided by 4. 0.075 divided by 4, and then add it to 1, which is 1.01875 to the 200th power. Oh, wait a minute. Not 50 years. That kid will be dead. He'll be dead. 18 years. There we go. I was like, wait a minute, 50? 18 years. Whoa. So 4 times 18, 72, to the 72nd power. Now we have enough there just to divide by 1.01875 to the 72nd, right? So we're going to divide that. And we're going to see how much money it would take to invest in 875 to the 72nd power. I got that it's going to take us approximately $19,687.59. So if we had 20 grand sitting around, we could grow our money to 75 grand in the time that it takes that baby to grow up, and we have enough to pay for college, which is all something you should think about doing when you're in that stage of life. Okay, so that's just a very short application of all the things we're going